Hello and welcome to this water drop where we're going to be taking a look at InfoWorks ICM and in particular the 2D objects, polygons and lines and what they are, how to use them, kind of best practices around that. So let's get started. Who is this for? Modelers that just really need a crash course in 2D modeling and understand some of the different objects and approaches that could be used within InfoWorks ICM. And then taking a look at the workflow here, we're just going to go through and review what the 2D objects are, what they look like, how they need to be set up. Same thing with line objects. Also look at 2D zones and some of the meshing options there. And then finally run through a simulation and use some of those tools to be able to review the results of those 2D simulations. So here we have a pretty simple 1D, 2D network over on the right side, but over to the left of it is really what I was hoping to concentrate on today, where it's just some dummy objects that I've created, either 2D polygons or 2D polyline objects. So starting off with some of the polygons, looking at the building here, these can be used, of course, to represent buildings. The special thing that these have are the ability to include LED controls for green roofs. You can also raise these up and down to create the appropriate level of them. You can also limit the amount of drain capacity coming off of the roof, and that can either be lost or sent to the 2D mesh, and these can be sent to a variety of different model objects in the system, either nodes, links, or 2D point sources. Next up, we have the initial conditions. We have water quality that's going to be used for setting the initial concentrations of things, the initial conditions of sediment, so being able to set up the initial sediment transport parameters, the initial conditions for infiltration, which sets the amount of water in the soil initially, and then finally the initial conditions hydraulic zone, which can be used to define the initial level, depth, or velocity of water in the system. As you can see, there's not a whole lot of information associated with these. It's really just to define the space where this is all contained. On the modeling tree here, that's where you'll need to create this initial conditions 2D zone. So for example, if I just add in kind of a dummy one here, I get some different zone types in here. That zone ID is going to have to be associated with the ID of the polygon for the appropriate piece there. Next up, we do have mesh level zones and mesh zones. These are pretty similar to each other. I'm going to start out with mesh zones here, though. The primary piece of this would be to override 2D zone minimum element area, so you can add in finer detail or coarser detail into certain areas. You can also use these to modify the ground elevation, so kind of similar to what we saw in the building object there. Of course, you don't get the added benefit of being able to do things like limit the amount of capacity coming off the roof or doing things like green roofs. Mesh level zones are, like I mentioned, fairly similar. However, these can not only be used to modify levels, just like the mesh zones there, you can actually specify the elevations at each one of the vertices. So by being able to specify each one of those vertices, we're now able to do things like proposed grading, maybe adding in finer detail that didn't get caught with the DEM, different things like that. So being able to use those to do proposed swales, whatever else. So next up, we do have the permeable zone. So with the permeable zone, this is going to be able to limit the amount of transfer infiltrated water to a node. So as you can see here, we have this drains to node links, subcatchment, multiple links. You will have to use this in conjunction with an infiltration area. So with the infiltration area and the permeable zone, we have the infiltration area to tell it how things are infiltrating to the system, and then being able to have that, taking a look at that infiltration zone. These would be used for things like extended period analyses or doing rain on grid applications. Again, this is kind of just defining the area that we're looking at as far as the infiltration zone goes. And as I open up the infiltration surface, that's where the real details are going to be in terms of being able to set up the different kinds of methodologies, whether it's Horton or green amped or just a fixed or constant type of loss. These can also be accessed through the polygon window. So looking at the bottom here in the tab, we have the modeling objects that we're able to draw on the surface, in addition to some of those additional objects that we might need. So we've got the infiltration surfaces right here, right next to the infiltration zones. Going back to our model, taking a look at roughness zones. These are going to be needed for running a 2D simulation. You do have the option in the 2D zone to set a default Manning's in, so if you do have gaps in the data, or just want a quick and dirty kind of analyses, or even if the entire area is pretty similar in terms of land use, you could use the roughness there instead of using the roughness zones. Often I like to be able to pull in a land use data file, so being able to populate that information relatively easy through both the roughness zones to define the area, and then pull it into the roughness definitions to pull in what the Manning's in for it is. So looking at this, there are different bands that we can add in, so depending on different depths that we have in the model. So let's say it's a grassy area with some shrubs, maybe some higher canopy kinds of trees and things like that. As the roughness changes at those different depths, you're able to create those different bands in order to see those differences between the two. The other nice thing is we've recently added in this priority bar. This priority bar essentially says which one to use if you have some overlapping polygons. So if you do have a not so clean land use file or something like that, then you'd be able to just set the priority to say that this is the layer that I want to use for the roughness. Generally speaking, unless you have a really dirty land use file, there's probably going to be maybe some subtle overlaps and not going to matter too much in the calculations, but saves a tremendous amount of time in terms of cleaning up the data, not having to do all that. The last one in here I'll talk about is the turbulence zone. This one's actually an interesting one that I hadn't really taken much of a look at, but this provides a definition for internal friction that's created by turbulent transfer of momentum from eddies. These eddies are naturally occurring in different fluid patterns, and these affect these eddies have opposite directions, and they cause friction, which contributes to the Reynolds stress in terms of the Navier-Stokes equation, which is used in the 2D simulation. So if I pull up the turbulence model property objects here, I can see that I have some different options for vertical eddy viscosity, because as those eddies create more friction, the viscosity goes up. Same thing here with the horizontal, and some of the common ones here, like the Smagorinsky methodology there. This isn't a comprehensive look at all the methodologies for vertical and horizontal, just a few. So now starting to take a look at some of the 2D line objects, 2D boundaries. Obviously these are going to be used for upstream or downstream boundaries. These can be set for things like vertical wall or normal depth or dry, or they can be associated with things like level and flow information. So if we hop back to our look here, the title of the sub-event, which can be accessed through the profile properties, and then just naming that profile the same thing as the 2D boundary. Same thing with the level information, where we just look at the profile properties by right-clicking and selecting that object and naming the same thing there. Hopping back to our model though, those can be also set up in the 2D zone itself. So if we look at the boundary type here, we can set this to things like dry or normal condition or vertical wall, just like we had in the 2D boundary condition there. Of course, you can see that there's not a level option or an inflow option. Going back to 2D line source, very similar to the 2D boundary condition, although the 2D boundary condition does need to be associated with the edge of the 2D area there. And with the 2D line source, that can be just kind of anywhere in the model. It doesn't really matter. So again, being able to associate that with a inflow information, and then again going to the properties and being able to set that value, the name of the profile the same as the name of the 2D line source that we've set. Base linear structure, this is going to be used for looking at the basically defining kind of an area within the 2D space to be able to represent things like walls and weirs. They can be good for setting up break analyses for dams. We'll take a look at one of those examples in a second here. But they also can be used in conjunction with bridge linear structures as well as sluice linear structures. Both of these are kind of the same thing, but they're intended to define for bridge linear structures the bridge dimensions, coefficients, and location of the bridges. If we take a look at my model over here, I can see that I have the base linear structure on the back end here. It is being represented as a broad crested weir because it's the overtopping that I want to model there, and if I pull up the section data, I can see the underlying cross-section there and then the bridge up top there. If I take a look at the bridge linear structure, that's just going to be what it is there. These do get associated via the names, but it does come up nicely as a drop-down menu. As you add in base linear structures, you can just go through the drop-down menu and select the one that it needs to be associated with. Same thing with the section data. But being able to define the thickness and the invert levels and openings and different things like that with the bridges that you have in there. Similar idea with the sluice gates, but these are to define the sluice gate dimensions, coefficients, and locations. So I did want to hop over and take a look at one of the dam break analyses that I have set up here, where I am using a base linear structure. I am representing it as a wall, being able to have the section data representative of the dam, where we can see the top of the dam there, and then as it goes up into the hill. These can be set up in a variety of different ways. I've got a couple of different ways that I took a look at it, failing geotechnically or failing overtopping. These can be set up to be partially removed or fully removed. So the wall trigger, once that gets activated, if it's partial, then it's just going to be those parts that are affected by that area. So as the elevation gets to a certain point on a certain cell that's next to the base linear structure, then only that part will fail. And then you can also set it up to fully fail. So once that elevation occurs anywhere along the line, then the entire thing gets removed. Same thing with a couple of different options here, whether it's depth or velocity. Velocity can be useful for some other applications. Let's say it's a guide rail or guardrail that gets removed during a certain type of event. Those can be useful there. We can also set this up basically using RTCs. If you watch the other RTC water drop, I went over this a little bit, but being able to have an association between the different vertices along the line here with some table information that will specify the elevation of the vertice as we go through the simulation. Some of these ones on the outside don't really fail that much, but as we kind of trickle through here, as we're going through the different time steps, you can see that elevation changing there. So finally, taking a look at our final 2D line object here, the porous wall. This can be set up to represent a wall, of course, of a certain height or a certain level, or just infinite. This wall can also be set up to be able to fully or partially be removed. With that, of course, comes the different kinds of trigger methodologies, and similar to the base linear structure that we saw earlier, the same types of wall removal triggers can be set there. These can be useful for modeling, like I said, walls themselves, fences, by modifying the porosity value. They could also be useful for modeling guide rails or guardrails. These could also be good for representing buildings. If you think about how to model a building in a 2D space besides using the building object, or maybe some people change the roughness zones of it, you could modify this porosity value so that it would represent the amount of water coming through cracks between the windows or doors, just as a different way of being able to model that kind of system. Taking a look at some of the different meshing options that we have in the 2D space. In this example, I am taking advantage of what's called the terrain sensitive meshing. So if I open up the 2D zone here, we can see that I have the terrain sensitive meshing box checked on. That opens up some attribute fields, maximum height variation, some different things like that. There's also the maximum triangle area and minimum element area. But what the terrain sensitive meshing does is, if going through the meshing process, there's more than a 3-foot drop across one of these triangular areas, it will split that cell in half, and then so on and so forth through the meshing routine. That gives us a lot of detail in areas like ridges or the banks of the river, and not a whole lot of detail in some of the floodplain areas up here, really balancing the need for accuracy and timely simulations. Some of the other things that can be included in here, we do have a variety of different boundary conditions, as well as infiltration information or turbulence models, like we went over a little bit earlier, just to be able to mesh things. And then finally, the mesh generation type here. We have classic and clip meshing. Classic is really the method that's been a part of 2D simulations in InfoWorks ICM for a long time. Clip meshing was added 3 or 4 years ago now, and it's intended to help with nearly coincident points especially. It's also been seen to improve the time it takes to mesh the 2D area. So this is now the default. Clip meshing is now the default for 2D areas. But what it does is essentially goes through and ignores things like these buildings that would interact with the mesh and cause there to be elements attached to the different vertices. So it ignores all that stuff to begin with, and then goes through and clips all those things out. And so if you do have nearly coincidental points, it won't create very, very small elements or triangles in here, so that you're not bogging down your simulation unnecessarily. So now we're going to take a look at some of the objects that can be used in here to be able to review results. They are points, lines, and polygons. In here, I've already got these added in prior to the running the simulation, the different points in here. So I can come up here, graph things like the elevation or depth, or what kind of velocity might be going through them, some different options like that. I can also pull these up in a nice grid view. These were high watermark locations that were observed, so I could pull this this chart up very quickly to see the maximum element level in here, to be able to just copy and paste that onto an Excel sheet with those high watermarks there, just to see how well things are calibrated between the modeled and the observed data. Next, I can add in things like a line. The disadvantage here being that this is kind of a one and done type of object. So once I do close out this simulation, this line is going to go away, versus if I include it in the model like I did these points, it will come up with every single run and simulation. But it's very similar to the points. I can come up here. I can look at the depth along the line, or the flow that's going through the line, different objects like that. Same thing with the results and pulling up those line information, the max flow, min flow, the flow during the time step, some different options there. And then finally, we can look at polygons here. So being able to pull in that information as well. So if I just draw a polygon here really quick, adding in just a dummy kind of value there, that should pop up here soon. Or I guess it's, if I go back and go into try to graph something associated with this results polygon, I can see I have some different options here as well. Flow through polygon, area that's inundated. So here we go, I've got that pulled up. I can drag my status bar to any point in the simulation, and I can see how much flow is going through in this case.
So with that in conclusion, the main reason I wanted to put this together was because I think the more you know about the different objects within InfoWorks ICM, the better you can model, giving just some examples of ways you can use some of the different 2D objects within InfoWorks ICM, because I know a lot of our training and some of the resources out there don't necessarily have a lot of talk about the different 2D objects, and so just wanted to get that out there. And with if there's any problems with some of these objects, or just want to understand some of the techniques a little bit better, please feel free to reach out.